Hello, Chem 151 students, and welcome to week 7, where we're going to continue our discussion of chemical equilibrium. So it's chemical equilibrium part 2. And this week, we're going to divide our lecture into two main parts. The first will be about calculating equilibrium concentrations. And the second will be about an idea called Le Chatelier's principle, which is regarding what happens to equilibrium when there is a change in concentration, pressures of gases, temperatures. So the first lecture is going to be about calculating equilibrium concentrations. The second will be about Le Chatelier's principle. We won't have a third lecture this week, but the homework is quite extensive. The main point for this week is going to be to practice with problems. There's only so much I can lecture to you. I can show you the techniques, but what really needs to happen is you have to practice them. And so what I'm going to be doing is showing you several mathematical techniques that we will use to determine what the concentrations of reactants and products are at equilibrium if we are given the equilibrium constant for the reaction. So here's an example of a problem like this, where we use the equilibrium constant in order to determine the concentrations of reactants and products at equilibrium. So it says at 700 K, we've got 0.500 moles of HI, which is added to a 2-liter container and allowed to come to equilibrium. We will calculate the equilibrium concentrations of H2, I2, and HI at equilibrium. A reaction is given. H2 plus I2 is in equilibrium with 2HI, and Kc here is given as 57.0 at 700 Kelvin. Okay, so first thing is we should take a look at this equation, and we should think that we should be wondering in which direction is this reaction going to go. And then after we've determined that, we're going to do some math to figure out the equilibrium constant. The general procedure that we're going to be doing is first we'll write a balanced equation for the reaction. This time the equation was given to us. And then under the balanced equation, we'll make what's known as an ICE table. And ICE stands for initial concentrations, change of concentrations when it's going to equilibrium, and then finally E in the ICE is the equilibrium concentrations. So we'll make the table and we'll define the changes in terms of the variable X. Because we won't know what the changes will be, but that's what we're going to want to try to determine. And then we'll substitute our equilibrium concentrations, which are stated in terms of X, and solve for X. And then once we've solved for X, we can calculate the equilibrium concentrations, and we can substitute them into the equilibrium equation. So this is a quick rundown of the steps. I give you a more thorough analysis in a separate set of notes that I put up called the equilibrium concentration or equilibrium concentration solving guide, which I also put up on the canvas under the reading. So you should check that out to have some quick notes on how to do this. That just kind of summarizes in like a little over a page everything that I'm going to tell you here. So here we've got this problem and we've got this reaction here. So the K here is given for 57. What's interesting about this problem, and the reason why I picked it, is because we are given an amount of product here at equilibrium, but no reactants, which is interesting because it makes you think. You have to think about first in which direction the reaction is going to go. So we can start by writing down our equation here. We've got our equation. We'll make our ICE table. So underneath we have the ICE table. It stands for initial, change, and equilibrium. And we've got a space here for each of our reactants and products. And so if we read the question, we'll see that we don't have any H2 or I2 to begin with. So their amounts are going to be 0. And it's important to note here, although I didn't write it, that these are molarities, okay? Sometimes your table can be a little crowded, and so you'll leave off the molarities, but just keep in mind whether you're talking about molarities or maybe atmospheres if you're dealing with pressures. Finally, we have to put the concentration of HI, but we're not given the concentration, we're given the number of moles. So we should calculate the concentration of HI. I'm just going to do it up here in the corner. So the concentration of HI is going to be the moles over the liters. So it's going to be 0.500 moles over 2.00 liters. So that's going to give us a concentration of 0.250 molar. And that's what we're going to put right here in this box. Okay. At this point, we want to know which direction the reaction is going. So this is where you would want to calculate Q. Now, I won't always make you calculate Q. In this case, it's kind of trivial because we only have products. And so the products have to, make reactants. It's the only way this reaction can go. But it's always prudent to calculate Q, and I'm going to do it now. So our expression for Q would be products concentration of, HI, we'd square that, over the concentration of H2, also over the concentration of I2. And if we plug those in, we have 0.250 squared for HI, and then we've got 0 for H2 and 0 for I2. And so our Q is infinity because we're dividing by 0. So here Q is greater than K. So remember from our lectures last week, this means that we have too much product right now and not enough reactant to be at equilibrium. And so the reaction is going to go left or towards the reactants. And this is important because it tells us how we're going to define the change. So when it comes to the change, what this means is we're going to be losing product here and we're going to be gaining reactant. So we're going to make our X negative for the products and positive for the reactants because we're going to be getting more reactants. So we're going to call the amount that we get here plus X for H2. So this means, every time two of these react, they're going to make one H2. So this is really plus 1X. And every time this reacts, it's also going to make one I2. So the amount of H2 and I2 that are made are equivalent here. They're both, we can call them both X. Now, for HI, we're going to be losing this, and we're going to be losing it twice as fast as we make this. So what we put here is minus because we're losing product, and then 2X because every time two of these are used up, one of these are made. Now, another thing that I'll note here is that we're going to be doing stoichiometry in terms of molarities instead of moles. So always in the past, you've done stoichiometry in terms of moles. You've said, 1 mole of this is made when 2 moles of this react, or 1 mole of this is made when 2 moles of this react. But we're going to be using molarities instead because during this whole process, our volume, 2 liters, is not going to change. And so we'll be able to use molarities just as we would moles, because molarities is moles divided by liters. That's molarities, right? So if the liters aren't changing, then when we have moles per liter at the beginning and we add like some moles per liter later, if these 2 liters right here are the same number, then we can add these fractions no problem and we'll still have a molarity. And so it's going to be very, very common in equilibrium problems to get our concentration in molarities and just continue to do our stoichiometry in molarity. We're going to do it all the time. It just makes the problems easier. And we're going to use this technique very, very often in this class. Okay, so next, to get the equilibrium concentrations, we add the initial concentration to the change. This tells us we're starting here, we're going to get X more, and so at the end we'll have 0 plus X, or just X for equilibrium. And same for the iodine, we're starting with 0, we're going to add X more, so at the end we'll have X amount of iodine as well in terms of molarities. Now for HI, we're starting with 0.25 and we're going to lose 2X. So what we'll have at equilibrium is the 0.25 we started with minus the 2X that was used up. And so these are going to be our concentrations at equilibrium. At this point, though, we're going to have to plug these into the equilibrium constant expression and solve for X. That's our goal now. And so let's write out the equilibrium concentration expression. It just looks just like the Q expression here. So the K expression here is going to be our concentration of HI squared on top, and on the bottom we'll have our concentration of H2 times our concentration of I2. And so now what we're going to do is we're going to plug our equilibrium concentrations that are stated in terms of X. We're going to plug those in right there. So for HI squared, we're going to plug in 0.5 minus 2X. And that's going to be equal to Kc. So we're given the Kc here, it's 57. So we plug that in for the K. And now for the concentration of HI, we put in this amount right here, 0.25 minus 2X, and we're squaring that. And then we're going to plug in X, our equilibrium concentrations for each H2 and I2. So we get X times X on the bottom, which is X squared. So at this point, we're ready to solve for X. And so we're going to have to do some math here. And in this particular problem, we have the fortunate situation where we've got something squared over something squared. And you guys may remember from your algebra rules that this is equivalent to saying we've got 0.250 minus 2x over x, whole thing squared. Okay, so that's really useful to us because what that means is mathematically we'll be able to take the square root of both sides, and that will eliminate a quadratic for us, which we want to avoid. So a quadratic is a kind of formula that has squared x's in it, and it's more difficult to solve. We're going to have techniques for solving quadratics more easily, and then if those techniques don't work, ultimately we'll have to resort to the quadratic equation, which is a whole lot of work, so we try to avoid it when we can. Okay, so let's copy this over to the next slide here. So if we go to the next slide, we're solving for x, and we've got what we had here. So again, we can take the square root of both sides, which is what we're going to do here. Okay, and so when we take the square root of this side, we get rid of the squares, but on the other side, we'll have to take the square root of 57. So we'll take the square root of 57.0, and we get 7.55. So we're going to write 7.55 for this. So we got 7.55, and then we've square rooted both of these. And so now to solve for this, we'll want to multiply both sides times x. So we multiply both sides times x. That's going to cancel this x, and we'll just have an x over here. Okay, so then we're going to get 7.55x equals 0.250 minus 2x. Okay, and now what we want to do is we're going to add 2x to both sides. So we do plus 2x plus 2x. And this is exactly 2x, so we don't have to worry about sig figs here. We'll just keep it at our sig figs that we got for the 7.55. So this is going to give us 9.55x equals 0.250. And so finally now to solve for x, we're going to divide each side by 9.55. And so that will cancel our 9.55 here, and we'll get the value of x. So let's go ahead and do that. 0.250 divide by 9.55, and we get 0.0262. 0.0262. So that is x. And so now what we do is we go back and we say, okay, the concentration of H, let's just look back at the last slide real quick. So we've got our x. I'm just going to write it down on this slide too. So we found our x. Our x was 0.0262. And so our values of our concentration of x and I at equilibrium are equal, or of H2 and I2 at equilibrium are equal to x. So those are going to be our concentrations for H2 and I2. To determine the concentration of HI, we have to plug x in here. So that's what we're going to do on the next slide. So for the concentration of H2, it's equal to x. It's 0.0262 molar. For the concentration of I2, it's also equal to x. It's 0.0262 molar. For HI, it's 0.250 minus 2x. So we can plug that in. 0.25 minus 2 times 0.0262. And so we get 0.198 molars. And so that's our result. This is in my calculator's in scientific notation, but we just move the decimal 1 over. And so that's how you handle that kind of problem. Now again, this was a fortunate situation. This is kind of the easiest situation you might encounter. It's one where it is possible mathematically to take the square root of both sides, and then that clears your quadratic, which makes things all very easy. But it's not always that easy. Sometimes you do have to deal with a quadratic where you've got an x squared. And so what we're going to have is a special technique that we're going to use, which will allow us to avoid having to solve that quadratic by making a simplifying assumption. And so that's going to be the next example that I give you, the simplifying assumption. Okay. So sometimes, as I said, it's not easy to solve for x directly, so we'll regularly use a technique we'll call the simplifying assumption, or just the assumption, to simplify the math. And we're going to be doing this a lot throughout the class. This is probably the first time you've encountered a situation where you need to make an assumption to solve the math. So you can't even always use the quadratic, because sometimes you will actually get an x to the third power. And at that point, you can't just use the quadratic equation to solve it. It becomes very, very difficult mathematically. Sometimes it is basically not possible to solve analytically. But if we make certain assumptions, we can get a very close answer that is acceptable in error. And this is probably the first time you've encountered this, but if you are going to go into more advanced mathematics or physics classes or chemistry classes, this is going to be a strategy that you use quite regularly to wrangle in math that is unsolvable, essentially, without some assumptions. So what we want to do is, our main goal is we're going to look at K and see how big K is compared to the concentrations that we're originally starting with. So you guys know that K is essentially product concentrations over reactant concentrations, just to state it very simply. So if K is large, that means that the reaction is going to go very far forward and make a lot of products. And so if we're starting with only reactants, what that means is X is going to be quite large. There's going to be a big change. And what we're trying to do is hope for a situation where X is small. So small that it's very small compared to our initial concentration. So we can consider the change in our initial concentration to be very small and ignore it. And we'll have some error, but we hope that it's an acceptable amount of error. So the technique that we're going to use both a pre-check here for our simplifying assumption and a post-check to make sure that it was valid. So what we want to do is first check that K is small, so that we can assume X will be small. So we're going to want a K that's at least 4 times smaller than our initial concentration of reactants. This means the reaction will not proceed forward very far and X will be small. So we calculate our initial concentration divided by the K, and we'd like it to be at least 400 times greater. So if the initial concentration divided by K is greater than 400, we're going to assume that X is much, much smaller than our initial concentration. So if we are subtracting X from our initial concentration, essentially we're subtracting not a lot. So this is like if you have, think of it this way: if your initial concentration is 10,000 and your X is 1, well, then your result is 9,999, which is effectively almost the same as 10,000, right? So we're hoping that this here, if this is our X, that it's small compared to our initial concentration, so that when we subtract the X or the 2X, that it's such a small thing that we've subtracted that essentially our initial concentration remains unchanged. So this is going to introduce a small amount of error. Obviously 9,999 is not exactly the same as 10,000, but it's pretty dang close. We have a very, very small error when we assume that these are the same number. And so we're going to accept that error because it will make our math easier in many cases. But afterwards, we do want to make sure that our assumption was indeed valid. So this is a pre-check to see if we should even try to use the simplifying assumption. If this pre-check fails, chances are there's just going to be too much error involved in using the simplifying assumption, and we'll have to solve for x, probably using the quadratic equation. So after we're all done and we've solved for x using the simplifying assumption, then we're going to divide x over the initial concentration. And what we want is we want x to be no greater than 5% of the initial concentration. We're accepting a maximum of 5% error in this calculation. If x over the initial concentration is greater than 5%, then we're going to go back and use the quadratic formula to solve for x instead. Finally, if k is very large, the assumption won't work. But what you can do is you can reverse the reaction. If k is very, very large, that means the k of the reverse reaction would be very small. And so that's a little strategy that you can use, but that would only be if you're starting with products. That's why I say it's very situational. Because if you're starting with all reactants and you reverse the equation, x is still going to be big because it's going to go backwards very bigly. And so it's very situational, but this is one last ditch effort that you can sometimes use to salvage the simplifying assumption. It's not very common, but I do mention it because it is sometimes used. Even sometimes in the solutions in your textbook, they'll like go ahead and give that a shot. They don't really talk about that in your textbook until they use it in one of the solutions, but this is a strategy that can be used. Okay, so let's go ahead and do an example showing you how to use the simplifying assumption. Okay, so phosphorus pentachloride decomposes as follows. So we got this equation and we're given a Kp here. So we're going to be working in atmospheres this time, but it works exactly the same way. Okay, we'll calculate the equilibrium partial pressures of PCl5 if the reaction begins with PCl5 partial pressure of 0.18. So not only can we do this stoichiometry that we're going to do in terms of molarities, we can also do it in terms of pressure, because the pressure, as long as the volume doesn't change, the pressure is going to be directly proportional to the number of moles. And so we can use the pressure in place of moles. Another little trick that we use to make our calculations a little easier and faster, instead of having to convert to moles using the ideal gas law, then convert back from moles back to atmospheres. It's a lot of work, so we'd rather not do that. These problems are enough work as it is. Okay, so first thing we're going to do here is we'll set up our ice table. So we write out the reaction here, PCl5, and we've got, and I'll leave the phases off. They're all gas. We should note that, but they're all gas. We know that. And so we'll make an ice table. And our ice table here is going to be in terms of atmospheres. Okay, it's just something to keep in mind. Okay, and so in our ice table, we're going to have 0.18 atmospheres for the PCl5, and we've got no PCl3 and no Cl2. So again, you could calculate Q here. Why don't we go ahead and do that just for the hell of it? So Q is going to be the pressure, we're doing QP here, the pressure of PCl3 times the pressure of Cl2 over, I'll just use parentheses like we usually do, over the pressure of PCl5. And so if we put this in, this is going to be 0, this is going to be 0, this is going to be 0.18. So the Q here equals 0. So Q is less than K, the reaction is going to go forward. Of course, we know that just by inspection here, the reaction can only go forward. It can't go backwards. But I go through the process of calculating Q because sometimes you'll be given amounts of reactants and products to start with. So it will be important to know which direction the reaction is going to go. But here we do know the reaction is going to go forward because Q is less than K. And so we would say now here our change is going to be minus X plus X plus X. And these are all 1 because all the coefficients in the balanced equation are 1 here. So as a result, we're going to get for our equilibrium 0.18 minus X, and then X and X here. Okay, now what we'd like to do, I'll go ahead and plug these in now. So if we plug in for K here, so just like Q, K is going to be the pressure of PCl3 times the pressure of Cl2 divided by the pressure of PCl5. And what we'd like to do is we'd like to use a simplifying assumption. I'm going to plug these in. I'll get X times X, which is X squared on the top. X squared. And then on the bottom, I'll have 0.18 minus X. And our K is given as 3.4 times 10 to the minus 4. Okay, so K is pretty small here. And now we do have pressures, but we can do the same thing with pressures with Kp. So essentially pressures work for Kp's the same way that concentrations work for Kc's. So what we're going to do is instead of taking our initial concentration, we'll take our initial pressure. So we're going to do pre-check here, pre-check. And we're going to take that initial pressure, 0.18, and we're going to divide it, or rather, sorry, we're going to take our 0.18 here. We're going to divide it by 3.4 times 10 to the minus 4, and we want this to be at least 400. Okay, at least 400. So 0.18 divide by 3.4 times 10 to the minus 4, and we get 529, about 530. So this is greater than 400. So it looks like we're going to be okay. Of course, we don't know. All right, we don't know for sure that it's going to work out. We're going to have to do a post check too. But the result is we're going to now assume that 0.18 minus X, we're going to say that is approximately equal to 0.18. Okay? Because subtracting the X is going to be so small that it's not going to change the value significantly. So what we're going to have here now is we're going to write this instead as X squared over 0.18 equals 3.4 times 10 to the minus 4. Okay. All right, so now we need to multiply both sides times 0.18. So let's do that. So we're going to multiply, so we go times, so we're going to go times 0.18 on this side, which is going to cancel these, and times 0.18 on this side. And so let's calculate that. 3.4 times 10 to the minus 4 times 0.18. Now, I feel like I might have calculated this wrong, but I know it's still greater than 400. I want to double check that in a second. But here we get, okay. So now what we have is we have X squared on this side, and on the right we have the result of our calculation, which was 6.12 times 10 to the minus 5. And that would actually be with 2 sig figs, because the 3.4 has 2 sig figs. Okay, so I want to double check this. I feel like for some reason I thought that would be bigger. Yeah, maybe not. Yeah, I guess it's right. Okay, 530. That's fine. Okay, so now we're going to take the square root of both sides. So let's square root both sides. And so we're going to get x now. X equals, so it was 6.12 times 10 to the minus 5, and we're going to square root that. And so we get 7 with 2 sig figs, 7.8 times 10 to the minus 3. Okay, and so this is our x, and I mean, if you notice, this is probably, you know, pretty significantly less than 0.18. But what we should do is we should do now a post check. So now we did pre-check, now we're going to do post check. And in the post check, what we do is we check, well, how big is this compared to x? It needs to be less than, or compared to, how big is x compared to the initial concentration? It needs to be less than 5% of the initial concentration. So we're going to now do 7.8 times 10 to the minus 3 divide by 0.18, and we're going to multiply this times 100% to make it into a percentage. So it's we're going to divide this now by 0.18 and then times 100 to make it a percent, and we get 4.35%. So this is barely good enough. We are accepting a small amount of error here, but it does make the calculations much simpler. Now this one, you could have solved it with a quadratic and you could have gotten a slightly better answer. But some of them, especially if they have an x cubed, they will be impossible to solve with the quadratic. So you'll need to use this technique sometimes. So finally, we can get our answer. So our concentration now of, our pressures rather, of PCl3 is going to equal our pressure of Cl2. They're both the same, they're equal to x, and so they are 7.8 times 10 to the minus 3. And don't forget the units. Remember, our units here are atmospheres, and so we're going to write those units. We do have to say, you know, what are our units. So this is one of our answers here. And then the other answer is going to be 0.18 minus that, which should just be very close to 0.18, right? So the pressure, oh man, I wrote behind my head, but you guys get it. PCl3 equals to x, yeah, it's the same as x. Okay, sorry I wrote behind my head there. So I'll write the other answer up the top, since so I don't write it behind my head. I should have written the other one up there. But so the pressure of the PCl5 is going to be 0.18 minus x, so it's going to be 0.18 minus 7.8 times 10 to the minus 3. 0.18 minus 7.8 10 to the minus 3, and so we get, you know, 0.17, right? If we round it to sig figs. So the pressure of PCl5 is 0.17. So this is an example where, oh, and atmospheres, don't forget the unit. This is an example where, yeah, you know what, the result wasn't so great, right? We did have about, you know, 4 point something % error, but this is an acceptable level of error, especially if it's the only way we can get an answer, which happens sometimes. So that's the way you solve using the simplifying assumption. And so again, it was very important that we did this post check, right? Sometimes it will be the case too that your pre-check passes, but your post check fails. Which is kind of the worst, because then you have to go back and solve the quadratic, and after you've already solved everything using the simplifying assumption. So some people just, when they can use it, the solving for the quadratic, they'll just jump ahead and solve the quadratic. You can always solve the quadratic if you have a quadratic equation. But if you don't, if you have, you know, to x to the third power to the fourth power, which can happen sometimes, then that's not even an option. You really have to use the the simplifying assumption, or it just cannot be solved analytically. You have to use some types of assumptions. There are more advanced assumptions we won't go into. You won't have a problem like that where it's impossible to solve. There's going to be either the simplifying assumption or the quadratic. You can solve it either of those ways. Okay. So that's the answer. This is in fact problem 17, sample problem 17.9b in your textbook. It's not the one where they write out the solution with the explanation, but this is the solution at the end of the chapter. So that for I do highly suggest the sample problems for this, maybe even before you go for the homework. So make sure to attempt the problem. They give you the full solution in the textbook, and then I'd say go for the sample problems, because they give you pretty decent solutions at the end for these, not just an answer at the end of the chapter, right before the chapter problems. So for these, very difficult mathematical problems, very highly recommended to use those sample problems with full solutions, maybe even before you go for the homework, or at least if you're preparing for the exam and you haven't done them yet. It's really good that they're good examples. So if the other strategies won't work, so we've seen two strategies now. One strategy is we take the square root of both sides. Sometimes you can take the cube root of both sides. It can happen. If you can take a square root of both sides, that's the easiest way. Otherwise, you probably use the simplifying assumption. And then if that doesn't work, you have to resort to the quadratic equation. Of course, you can always refer to the quadratic equation. Here, you guys have your own notes for the exam. It's all of our notes, exams online are open notes, so you can have this equation in your notes. I generally give it on exams. You don't have to memorize it. It's not math class, but you do have to know how to use it. And so now we're going to talk about how to use the quadratic equation. So we're going to have, in fact, the same problem. This is an interesting thing too. I chose the same problem on purpose. It's because whether or not this is going to work depends on the initial concentration, right? The big difference between this problem and the last problem is that the initial concentration is smaller, and so we're not likely to pass our pre-check. In fact, I'll just go ahead and do our pre-check right now. Let's go ahead and do it. I'll do it up here. I'm going to need all the room I can get on this slide. So for our pre-check, here, we do, again, we want the initial concentration or initial pressure in this case, either way, over the K to be greater than 400. So this is going to be, this time, 0.025 atmospheres is the pressure, divided by our K, 3.4 times 10 to the minus 4. Okay, and so when we calculate that, this time, 0.025 divided by 3.4 times 10 to the minus 4. We get 74-ish. 74. That's less than 400. We cannot use the simplifying assumption on this problem. So if it comes to the point where we're going to have to solve a quadratic, we're going to have to solve the quadratic. We have to use that to solve for x. So let's go ahead and give that a shot here. We'll have the same ice chart as before. So it's going to be, we write our equation PCl5 in equilibrium with PCl3 plus Cl2. We're doing an ice table. Again, good reminder is that these are in atmospheres, okay? Make sure to remind yourself of that. And so we're putting our atmospheres of PCl5 here, and we've got no products. So again, we calculate Q again, but it's the same, it's 0. It's less than K, the reaction is going forward. So we put minus in front of the reactants, plus in front of the products. And since it's one for all of these, it's going to be minus X plus X plus X. And so for our equilibrium concentration, we have 0.025 minus X here, and then X and X. Okay. And so now we're going to, plug this in to our K. So it's, It's going to be the products over the reactants again. So Kp here is going to be the pressure of the PCl3 times the pressure of the Cl2 over the pressure of the PCl5. And so this is going to be x times x on the top, which is x squared. And on the bottom, it's going to be 0.025 minus x. And this is going to be equal to 3.4 times 10 to the minus 4. Okay, so we're going to have to use the quadratic equation. So let's go back to the last slide and look at the quadratic equation. So what it says is that we need to put the equation in the form 0 equals ax squared plus bx plus c, where a, b, and c are numbers, constants. And x will have the value of negative b plus or minus b squared minus 4ac divided by 2a. Notice we have a plus or minus here. What this means is that we're solving a quadratic, so we actually get two values, okay? And it will generally be the case that the negative value, we will throw it out. It won't make any physical sense. I'll show you why. Whichever value is negative, that's going to give us a negative concentration if we have a negative x for our products. But you can't have a negative concentration of something. So generally, when the x comes out negative, that one you can throw out and you use the other one, which has a physical meaning to it. So here what we're going to have to do is multiply both sides by the bottom of the fraction here, which is 0.25 minus x. So if we multiply both sides by that, we're going to get x squared equals 3.4 times 10 to the minus 4. And then we multiply both sides by this, 0.025 minus x. So when we multiplied by this on this side, it canceled. And we had just x squared here. And then on this side, we had 3.4 times 10 to the minus 4 times 0.025 minus x. Okay, now we're going to distribute this. So we're going to multiply 3.4 times 10 to the minus 4 times 0.025 and times negative x. And so we will get x squared equals, so let's calculate that, 3.4 times 10 to the minus 4 times 0.025 equals. And this gives us 8.5 times 10 to the minus 6. So we're going to have here 8.5 times 10 to the minus 6. And then this will be minus 3.4 times 10 to the minus 4x. Okay. Now remember, we got to get our quadratic equal to 0 to be in the quadratic form. So what we're going to do here is we're going to add 3.4 times 10 to the minus 4x to both sides, and we're going to subtract 8.4 times 10 to the minus 6. So I'm just going to write that so you see it. So we're subtracting 8.5 times 10 to the minus 6. We're adding 3.4 times 10 to the minus 4x. And so these will cancel. And we're going to add the same things to the other side. So overall, we get the equation x squared equals, and we're going to subtract this from this side too. Whoops, not equals. So what we did was we added 3.4 times 10 to the minus 4x to the other side. So we're going to have plus 3.4 times 10 to the minus 4x. And we're going to have minus, since we subtracted 8.5 times 10 to the minus 5. So 8.5, or sorry, times 10 to the minus 6. That's a 6 there. Times 10 to the minus 6. Okay, and then on the right side, we have nothing left. We subtracted everything, so that all equals 0. So in our quadratic, we haven't written a 1 here, but there is a 1, even though it's not written. So A is 1, so that's this right here. B is 3.4 times 10 to the minus 4. And C is negative 8.5 times 10 to the minus 6. Don't forget the negative there. That's really important. Okay, so now we have to solve the quadratic. And so we're solving the quadratic here. X equals minus b, so negative 3.4 times 10 to the minus 4, plus or minus So we're going to have to do two things right up there. B squared, so 3.4 times 10 to the minus 4 squared minus 4ac, minus 4 times 1 times negative 8.5 times 10 to the minus 6. And this is going to be all divided by 2a, so 2 times 1. So what you want to do first is to calculate the whole right side of the plus or minus here. So this whole square root, we want to calculate that first, because then we're going to have two results. And this is not 2x, sorry, it's 2 times 1, because a is 1. Okay, and so now we're going to want to calculate this whole thing that's underneath the square root, because then we're going to get two results, one with the plus and one with the minus. Okay, so it's going to be 3.4 times 10 to the minus 4, and we're going to square that. And then that's going to be, so here we're going to have a negative, so we're going to have minus, but we're going to be multiplying times something negative. So that's going to affect that. 4 times 1 times negative 8.5 times 10 to the minus 6. Okay, so we get that. And that, and we get a, a positive here. We had to get positive because we're adding, so it's minus and negative, so we end up adding something. And we want the square root of that, so square root of the answer there. Okay, and so now we can write down what we've got. So it's 5.8 times 10 to the minus 3. So we got plus or minus 5.8 times 10 to the minus 3. This is going to be, so x equals negative 3.4 times 10 to the minus 4. And that's over 2. Okay, so now we can see here that if we do the subtraction, we're going to get a negative number. So we can basically ignore the subtraction part. And we're only going to do the addition because this is negative. So if we add a negative number to it, if we subtract, we're going to get something negative. A negative x doesn't make sense. So we can just do the positive. And so we're going to get now x equals, and so now let's add these. So we've got this result, and we're going to add a negative. So I guess we'll say we'll subtract 3.4 times 10 to the minus 4. Okay, and then we divide by 2. And so we get x is 2.7 or 2.8. 2.8 times 10 to the minus 3 is our x. Okay, so now we're ready to calculate our concentrations. So we see that, and I can just put them over here. So our concentrations of PCl3 and Cl2 are going to be, so concentration, or rather not concentration, pressures of PCl3, it will be equal to the pressure of Cl2, which is equal to x. So those equal 2.8 times 10 to the minus 3 atmospheres there. And then for our pressure of PCl5, that's going to be 0.025 minus x. So that's going to be 0.025 minus 2.8 times 10 to the minus 3. And so that's going to be equal to, I'm just going to type it in normal notation, 0.025 minus 0.0028, right? And we get 2.2 times 10 to the minus 2, or 0.022. 0.022. And so that, and that's atmospheres. So that is our pressure of PCl5, and this is our pressure of PCl3 and Cl2. And so you can see that it's significantly more work to solve with the quadratic equation. It's not ideal. This one problem took me almost half the lecture. And so this is something, you'll practice a few times. I tend to try to avoid it. I'm just going to be honest with you. I tend to try to avoid anything this long on the exams because there just isn't a whole lot of time. But you should be able to do this. I can put it on the final exam. If I do put one, it's usually on the final exam where you have more time. And so those are the three ways in which you will mathematically solve for equilibrium concentrations if you are given the equilibrium constant. So number one is take the square root of both sides. Could be the cube root sometimes, but that's the easiest way. Number two is using the simplifying assumption. And number three is, if necessary, to use the quadratic equation. So I've given you lots of practice problems this week. I want you to make sure you get started on those a little early so you can ask me questions in the office hours. And so the next lecture is going to be about Le Chatelier's principle. A good deal easier, not a whole lot of math there. And so I'll see you in the next lecture.